Let's talk about the engine underneath Node.js that makes asynchronous I/O possible, libuv. When you write code in Node.js that reads a file, makes an HTTP request, or performs a DNS lookup, you are not calling the operating system directly. Instead, Node.js delegates all of that work to a C library called libuv. Libuv is an open-source, cross-platform asynchronous I/O library. It was originally written specifically for Node.js, but it has since been adopted by other platforms and languages such as Lua and Lua. The key design goal of libuv is simple but important: use the best possible I/O mechanism available on each operating system while exposing a single, consistent API to the layer above. On Linux it uses epoll. On macOS it uses Q. On Windows it uses IOCP I/O completion ports. The developer writing Node.js code never has to know or care about any of these differences. Libuv abstracts all of that away. Now here is something critical to understand about the architecture. Libuv does not depend on V8, the JavaScript engine. They are peers. If you look at a diagram of Node.js internals, Node.js itself sits at the top level, and directly below it are two separate pillars, V8 on the left handling JavaScript execution, and libuv on the right handling I/O. They do not talk to each other directly. Node.js coordinates between them. This distinction matters enormously for performance analysis. When you profile a Node.js application and spot a bottleneck, you need to know whether the slow part lives in your JavaScript code, which would show up in V8, or in the I/O layer, which lives in libuv. Treating them as one blob gives you misleading diagnostics. Libuv is responsible for network tasks including TCP and UDP sockets, DNS requests, file system operations, and executing child processes. Every time you use Node.js's FS module to read a file, or the net module to open a socket, or the DNS module to resolve a hostname, that work is coordinated by libuv. Now let's go deeper into how libuv actually manages concurrent work, because this is where the magic and the confusion both live. Node.js is single-threaded. Your JavaScript code runs on one thread. There is one event loop, and it processes one task at a time. But libuv is not single-threaded. Libuv maintains its own thread pool, and it uses this pool to handle work that would otherwise block the main thread. Here is how the flow works. Your JavaScript code runs inside the event loop. When your code makes an I/O request, say, reading a large file, it does not sit there waiting. Instead, Node.js passes that request to libuv, which assigns it to a thread in its thread pool. Your JavaScript code continues executing. Libuv runs the file operation in a background thread. When the operation completes, libuv fires an event back to the event loop. Your callback is then queued and will run in the next iteration of the loop. This design is intentional and clever. The thread pool is sized to be fast. By default it has 4 threads, configurable via the uv_thradpol_size environment variable. The pool is designed to avoid the overhead of creating and destroying threads too frequently because thread creation is expensive. So libuv keeps a stable pool of worker threads available and reuses them. The visual model for this is, your code runs in the event loop in green. Libuv's threads run in blue in the thread pool. When libuv has a result ready, it sends an orange event notification back to the event queue, which gets picked up by the event loop in the next cycle. This distinction is what lets Node.js achieve non-blocking I/O even though it has a single-threaded JavaScript runtime. The I/O is not blocking because it is not happening on the main thread, it is happening in libuv's thread pool. Your JavaScript just registers a callback and moves on. Understanding this model is foundational before you profile any Node.js application. A slow file system operation will show up differently than slow JavaScript computation. One is a libuv bottleneck, the other is a V8 bottleneck. Knowing which is which tells you exactly where to focus your optimization effort. Now that we understand the architecture, V8 handling JavaScript, libuv handling I/O in a thread pool, let's talk about what this means when something in your application is slow. There are 3 distinct categories of bottleneck you need to be able to identify. First, a Node.js or V8 bottleneck. This means your JavaScript code itself is spending too much time executing. The event loop is being blocked. Expensive computations, deeply recursive functions, large synchronous loops, these are V8 bottlenecks. While V8 is grinding through your JavaScript, the event loop cannot pick up new events, cannot respond to incoming requests, cannot fire waiting callbacks. Everything stalls. Second, a libuv or I/O bottleneck. This means the I/O operations themselves are slow. Maybe the disk is under heavy load. Maybe the network latency is high. Maybe your DNS resolution is taking too long. These problems live in libuv and the thread pool. The important thing to understand here is that these operations do not block the event loop. Your JavaScript keeps running. But if your application is waiting on many slow I/O operations, throughput suffers not because JavaScript is blocked, but because callbacks are arriving slowly. Third, a system-level bottleneck. The operating system itself, kernel call latency, physical hardware limits, these can cause slowdowns that neither V8 nor libuv can work around. When you start profiling, which is exactly what this chapter is about, you use tools like the V8 tick processor, perf on Linux, dtrace on Illumos and macOS, and flame graphs to visualize exactly what is happening. The profile output will tell you where the CPU time is actually being spent. If you see your own JavaScript functions at the top of the profile consuming most of the ticks, that is a V8 bottleneck. If you see kernel calls or libuv internal functions dominating, that points toward an I/O issue. This mental model is the foundation of everything we will cover in this chapter. Keep it in mind as we move into hands-on profiling with a concrete example.